speed of gravity is faster than light. In this abstract, we explore the properties of matter and energy and how much they can be compressed. We can understand that the radius of matter in its minimum state is about almost half of the Schwarzschild radius. When we calculate the escape velocity at this radius, we get a constant value of 4.24 into 10 raised to 8 meters per second for any given mass. The escape velocity at Schwarzschild radius is equal to the speed of light. Using this value, we can conclude that the speed of gravity is faster than light. It is clear that the Schwarzschild radius is not the actual radius of the mass. The Schwarzschild radius is the distance from the center of a mass to the point in spacetime where even light cannot escape from it. So, the matter can shrink further than the Schwarzschild radius. This idea mainly evolves from my published article, The Structure of the Relatively Accelerating Universe. This will provide a significant boost to our efforts in space exploration. This will enable us to significantly increase the speed of spaceships even further. The general theory of relativity explains how an object is precisely situated in spacetime. This concept extends it further. At the core of this concept is how an object utilizes spacetime. The interaction between matter and spacetime forms the foundation of our universe. That phenomenon is what we know as gravity. That's why Einstein regarded spacetime as a dimension. All matter always carries with it a corresponding amount of spacetime, proportional to its mass. This is the insight I gained from a thorough observation of the universe. It has the potential to alter our current conception of the universe. For that, we must comprehend the dimensions of both spacetime and matter. Here, I am using Planck units to develop the idea. I consider a unit Planck mass as a system. The key idea of this concept is that the unit Planck mass perfectly fits into the Planck volume, leaving no free space inside this system. Therefore, the radius of this system will always be equal to the Planck length. Let us examine how this system relates to its spacetime. According to this concept, we can say that Planck mass is equal to Planck length cube. If the Planck mass is equal to Planck length cube, then the quantist value or strength of Planck length concerning Planck mass will be as follows. Planck length is equal to cube root of Planck mass. In the figure, the inner sphere represents the amount of matter contained in a system. The outer sphere represents the spacetime that the mass inside can influence. Here, matter possesses three dimensions like length, width, and depth, as well as mass. These three dimensions also apply to spacetime. There, space and time interact with each other according to the amount of matter contained in that system. At the outermost part of the image, you can see that the amount of space that mass can influence is zero. But there, time is at its highest strength. It is the endpoint of spacetime under the influence of matter within that system. Here, time can reach its maximum velocity. It can be observed that the strength of time decreases and the strength of space increases as we approach the matter that is part of the system. This phenomenon is a result of the increasing influence of matter on space. Decrement in the strength of time and increment in the strength of space occur in the same proportion. So, the strength of time and space are equal inside the system. Since the strength of space is highest at the surface of matter within the system, the strength of time becomes zero. So the quantist values or strength of length or space and time are equal. So the quantist value of Planck time is also equal to the cube root of Planck mass. If we consider matter alone, we can see that it also has three dimensions, just like space. However, time has no significance in that context. It will contain only matter. Nothing can enter or travel within it. Time is meaningless where it cannot be traversed. A similar situation occurs in a black hole. Inside a black hole, matter shrinks to its minimum volume. Let's examine what happens when an atom is absorbed by a black hole. Inside the nucleus of an atom, there is a lot of space between the protons and neutrons. There is even more space available between the nucleus and the electrons. When an atom is absorbed into a black hole, its constituent particles are compressed to their smallest possible state within the black hole. The space inside the atom is absorbed into spacetime of the black hole. Here, a distinction is made between matter and spacetime. Now, we can try to find out the actual radius of a black hole when it shrinks to its minimum volume. So, we can use the formula 4 by 3 pi r cubed to find the volume of a sphere here. But we know that objects have different masses. Adding each unit of Planck mass will correspondingly add a proportional amount of spacetime to the system. To elucidate the nature of larger objects, their mass must be compared to the Planck mass. Therefore, it is necessary to understand the quantity of Planck mass contained within the object. We can quickly comprehend it by using this equation. Now we will see an equation ma rho is equal to mass divided by Planck mass. Here ma rho represents the ratio of Planck mass within the object, m represents the actual mass of the object, and m rho represents the Planck mass. Ma rho is variable according to the mass of the object. We can further extend equation 1 to describe objects containing more than one Planck mass and find the volume of the object. Vt is equal to 4 by 3 pi ma rho L rho cube. Here, L represents the Planck length and ma rho L rho is the radius of that object. This is because adding each unit of Planck mass to a system increases its corresponding Planck length. We already know the Schwarzschild radius is 2 gm divided by c square. This radius ma rho L rho will be the actual radius of any mass if it shrinks to its minimum. So, with this equation, we can find the actual radius of any mass. For example, if we calculate the Schwarzschild radius of the Planck mass, it would be 3.22724978 into 10 raised to minus 35 meters. It is roughly twice the Planck length 1.616 into 10 raised to minus 35 meters. So it has already been proved in quantum mechanics that the actual radius of any mass is not equal to the Schwarzschild radius. More information regarding this is recorded in table. In this table we can see the minimum radius and Schwarzschild radius of Planck mass, electron, Sun, and Earth. We can find the minimum radius is approximately half of the Schwarzschild radius. It is clear that the Schwarzschild radius is not the actual radius of the mass. The Schwarzschild radius is the distance from the center of a mass to the point in spacetime where even light cannot escape from it. It depends upon universal gravitational constant, mass of the object, and speed of light. So it can be said that the Schwarzschild radius is the minimum radius to which a mass must be compressed for it to become a black hole. If the mass is contained within this radius, the escape velocity at the surface would be equal to the speed of light, meaning not even light can escape the gravitational pull. So at this point the speed of gravity and the speed of light are equal. So, if the mass can shrink more, the gravitational force will increase. The speed of light cannot increase because it is constant. We can clearly say that the mass can shrink more than the limit of Schwarzschild radius, because the Schwarzschild radius is almost double of Planck length. Anyhow, here we have found the equation to calculate the minimum radius which a mass can ever achieve. So if we calculate the escape velocity with the minimum radius of a mass, we will get a constant value 4.24 into 10 raised to 8 meters per second. So with the result we can say that the speed of gravity is faster than light. And the maximum speed which gravity can achieve is 4.24 into 10 raised to 8 meters per second. Now, we can scale and describe the entire universe in one dimension. I have described the dimensional arrangements within a system in my book, Key to the Secrets of the Universe. Now let's apply this concept to the equation E is equal to mc square, focusing solely on mass and volume. Here, we can start again with a unit of Planck energy E rho is equal to m rho into L rho divided by T rho square. Let's examine how it can transition into either a particle or a grandiose structure. This equation describes a system comprising both matter and spacetime. Matter can exert an effect on spacetime proportional to its mass. Just as we know that energy cannot be created or destroyed, spacetime also cannot be created or destroyed. I have already stated that c square or L rho divided by t rho the whole square represents the amount of spacetime that a unit Planck mass can influence. We have already derived the quantized values of Planck length and Planck time in this theory. Indeed, applying the quantized values of Planck length and Planck time to the equation E is equal to mc square will lead us to intriguing insights and revelations. E is equal to m into the cube root of m rho divided by the cube root of m rho square. It can be understood that the quantized value of spacetime, the cube root of m rho divided by the cube root of m rho the whole square, is 1, which indicates a fundamental and indivisible aspect of the universe. We can understand that the distribution of energy in spacetime is uniform everywhere. That is, spacetime under the influence of mass is uniformly distributed everywhere. Let us imagine any point in spacetime as an example. Where the distribution of space is more, the distribution of time is less. The distribution of time is proportional to the distribution of space. If we add the strength of space with the strength of time at any point of spacetime, it will always be a constant value. This implies that the effect of energy on spacetime is uniform throughout the universe. This concept is the only way to reach quantum gravity. That is why our universe exists, based on the influence of gravity. Gravitation would not be possible if the influence of energy of two different objects on their respective spacetimes were different. The biggest example of this is our solar system. If the Sun's influence on its own spacetime and the Earth's influence on its own spacetime were in different proportions, the Earth would not be able to exist within the Sun's spacetime. We have already discussed how the strengths of space and time work inside spacetime with Figure 1. Therefore, at any point the distribution of spacetime will be the same. So, the graviton, the particle responsible for gravitational interaction, can maintain its mass precisely anywhere in spacetime. Upon reaching the surface of the outer sphere, the distribution of space becomes zero, and the distribution of time becomes its maximum. This does not mean that spacetime or gravity ends here, because the distribution of spacetime is still the same. Because time here holds the strength of spacetime and continues to do so. It's just that the influence of that particular mass on spacetime from that point is zero in the three spatial dimensions of length, width, and height. The spacetime of any mass is always bound to the spacetime of the universe. We can understand that the dimension of time plays an important role in connecting two different spacetimes. The proof of this is that the strength of space in outer space is very weak. As an extension of this idea, I have already calculated the estimated radius of spacetime of each of the above objects. But this time I am unable to present it here. Because while I am calculating the escape velocity, there seems to be some mismatch. I hope I can clear it as soon as possible. This situation can describe the entire universe. We can use the same situation to explain the behavior of an atom or a star. Then we must also consider the space inside the atom or star as part of the spacetime of the system. When we look at the volume of space inside an atom or star, the beginning of their spacetime is near their center. Here, matter and spacetime are part of one system, but they are two separate entities that can never merge into one. To test this, let's examine how spacetime functions in two distinct scenarios. Let's first closely observe the planetary motion of Earth around the Sun. Earth lies within the gravitational field of the Sun, which is a curvature in spacetime caused by the Sun's mass. So, indeed, Earth exists within the spacetime framework influenced by the Sun's gravity. Similarly, Earth also creates its own gravitational field, which is a curvature in spacetime with similar characteristics to that of the Sun. The position of the Moon is within Earth's spacetime. That is why the Moon can move along with the Earth. That is, along with Earth, its spacetime also orbits the Sun. Similarly, the Moon also has a similar spacetime. Here we can observe three different spacetimes, each of them moving along with the masses that influence them. Now let's consider another scenario for examination. Imagine that you are throwing a stone into an ocean. Here the stone is sinking into the water by leaving its spacetime to the Earth's spacetime. Archimedes' principle provides evidence supporting this situation. If spacetime of the stone were to immerse in water along with it, there would be a separation between the water and the stone. However, in reality, this separation does not occur. Here, the stone contributes its spacetime to that of the water as it sinks into it. If we take the stone out of the water, it can return to its original spacetime state. Matter merges with matter, and spacetime merges with spacetime. Exactly, this concept is analogous to what occurs in phenomena like the photoelectric effect and black holes, where the interaction between particles or massive objects leads to the exchange or merging of spacetime properties. In the photoelectric effect, when an electron absorbs a photon, its spacetime is added to the electron's spacetime. Similar phenomena occur in black holes. Now we can understand, with examples, that matter can utilize its spacetime in two ways. A photon traveling through spacetime can also interact with spacetime in this manner. A photon can travel while retaining its spacetime properties, or it can move freely by merging its spacetime with the spacetime through which it travels. We need to delve into a more detailed understanding of spacetime. Conclusion. In summary, the concept of spacetime provides a unified framework for understanding the interconnected nature of space and time. Matter influences spacetime, and in turn, spacetime influences the behavior of matter. Through examples like planetary motion, the photoelectric effect, and black holes, we observe how matter and energy interact with spacetime, exchanging properties and shaping the dynamics of the universe. This holistic perspective challenges traditional notions of space and time as separate entities, emphasizing their inseparable relationship within the fabric of reality. As we continue to explore and unravel the mysteries of space-time, we gain deeper insights into the fundamental nature of the cosmos and our place within it. A better understanding of the distribution of space and time in space-time will indeed facilitate our space journeys, enabling more precise navigation, planning, and optimization of space missions.